Hello everyone. Let's resume our class of foundation engineering. Okay, still on chapter 1. And in this video, we will talk about concept of unsaturated soil mechanics. Yeah, this part is also a very important part because sometimes or very often actually we have to build our foundation on unsaturated soil. And the unsaturated soil mechanics is a little bit complicated, more complex than fully saturated air or dry soil. Okay, so in this video, we will try to bring some concept, some definition, some lightning on this concept of unsaturated soil mechanics. Okay, so let's consider this kind of situation. As you can see here, this vertical cut of soil, vertical view, we have here the impermeable soil layer, maybe rock, for example, and this is a aquifer, means the water is confined in this area. Okay, so some of these aquifers sometimes they can be like this permanently. Okay, and the flow is like this, and the level of the water is here. Groundwater, water table is here. If we have this kind of situation, up to certain distance from the top of the water, like this, we have a zone that the water is not actually going there, is not reaching there, but the capillarity is making this place like wet also. Okay, and in this kind of situation, we can have this in this zone a certain part of the soil that is unsaturated. Okay, so this zone at some time at the top, if you have to maybe dig and place your foundation somewhere here, because you cannot build your foundation directly on the ground like this, there has to be at least a certain depth. So it means we will have our foundation in unsaturated soil. Okay, unsaturated soil, and there are a lot of consideration, a lot of concept, a lot of parameters to consider, because in this unsaturated soil, you don't have only water. Water and air both exist in this zone. The void in the soil mechanics, you know from the soil mechanics that the soil has the solid part between the solid particle of the soil and void in the soil. The void can be full of water or air or mix of these two. So if the soil is saturated, it means the void in the soil are full of water. If the soil is dry, it means the void in the soil are empty of water. There is no liquid. It's not always water. It can be any other liquid. Okay. So our concern here is how do we calculate our foundation when we build the foundation on unsaturated soil. Okay, so before we do some calculation, on this kind of foundation, you have to know what is unsaturated soil and what parameter you should consider when you are dealing with foundation on unsaturated soil. Okay, so let's talk about effective stress. Effective stress in unsaturated soil. So unsaturated soil, as I was saying, are commonly in building site, but the unsaturated soil mechanics is sometimes neglected in geotechnical engineering. People don't really consider it. Okay, so it's overlooked, and many problems are taken addressed assuming that positive pore water pressure is happening, even though in reality we have suction. So we will talk about this suction very soon. Okay, so understanding this unsaturated soil, it requires considering hydraulics, mechanics, and interfacial physics. Interfacial physics, because uh, this is why actually the unsaturated soil mechanics is a little bit complex because of this. You have to consider all this hydraulic, mechanics, and interfacial physics. So soil saturation, it changes, it varies with capillarity fringe above the water table. Can you see here capillarity fringe? This line, okay? This line is capillarity fringe. This line is limiting the capillarity. The water table is here, this level, but this zone, okay, capillarity fringe. So the saturation will depend on this line, okay? And the reduction, this and reduce pore water pressure near the surface. So the pore water pressure will decrease when we go near the surface, okay? And this decrease is due to evaporation. So the saturation of this zone, the degree of saturation will depend on this capillary fringe and will depend also on the pore water pressure, the decreasing pore water pressure when you get near to the surface, okay, due to evaporation. So this will induce suction and eventually desaturation, means the degree of saturation will turn to zero. Okay, it's important for you to understand everything that you need to consider when you have foundation, this kind of soil. Let's keep this just here. If we try to zoom in this zone, the unsaturated soil, and zoom in this zone where the soil is saturated, okay, and zoom somewhere maybe very close to the surface or another soil when there is no water at all. You can see here, if the void in the soil is full of water, we have saturated soil. The blue part is water, and the soil grain are here. This is water. Dry soil, we don't have anything within the grain, the soil particles. Okay, this is dry soil. And then in this case, unsaturated soil, we have both water and air in the void. As you can see, this water exists. These two exist at the same time. Okay, and when you have this kind of thing, the air pockets here, you can see it making this S suction. This suction is the UA, which is the pore air pressure minus the pore water pressure, UA minus UW. Okay. And in unsaturated soil, the pore water pressure is negative. Okay. And since this is negative, negative minus negative will be positive, right? So that's why suction will always be positive. And this suction is somehow a force that is pulling the soil grain together. They hold them together. This force of suction is the reason why you can build this kind of castle on a beach, for example. See, this sand is not saturated, it's unsaturated soil. Because of this suction, you can build this. Because this suction is holding the soil particles together. Okay, so you can build at certain height without collapse of the soil because of suction, actually. Okay, when you see this on a beach, please remember this. So if we go now to see how the degree of saturation is related to the suction, this suction here, okay, and also hydraulic conductivity. As you can see here, this reference, okay, you can try to get this reference online if you want. Canadian Geotechnical Journal. Degree of saturation here, and we have suction here, okay? So we can see here the degree of saturation. When the soil is saturated, maybe the suction is 0. And when the saturation is decreasing, the suction is starting to increase, okay? Maybe all here, from here, when the significant decrease of saturation is starting, we call here the air entry value, AEV, air entry value. Okay, as you can see, in this zone, the soil is fully saturated. And this zone, as you can see in the soil particles, we have blue part is water and white part is air. So both air and water exist in this zone. It started here. When it started here, the air entry, we can see just 1, 2, 3, maybe small part of air in the soil, not that much. And here, it's increasing. The place occupied by the air is increasing. This zone will be dependent on the soil type. It doesn't mean that it will be always, the slope will be always like this. It depends on the soil you are dealing with, okay? But up to here, you will have somehow residual water content. This residual water content, like the water is on the soil particles, okay? Like the water is thick on the soil particles, but the majority of water is gone. That zone is called residual zone, okay? And we can say that the hydraulic conductivity is almost like same, okay? Decreasing when the suction is increasing. This is just for your information, okay? So the question now the big question is, what will happen if we have our foundation in this kind of soil? What formula will you use for this kind of, what formula of bearing capacity? If you know the formula of bearing capacity for uniform ground proposed by Terzaghi, then we can find there are some references that are proposing formula to obtain the bearing capacity of footing, for example, in unsaturated soil. Okay, this here is an example, okay, from the oldest one to the newest one, 2020. Okay, so this equation, ultimate bearing capacity, it includes a lot of parameters. The pore air pressure, the pore water pressure, okay, all of them are included. So NC, which is the bearing capacity factor, N gamma, okay, you can check all these references, but we will come back on these references later. Here, this part, this chapter is just review, okay? And when we start to do foundation on complicated soil, complicated ground, we will come back on this formula, okay? With more detail, okay? But you can go and check them. This one is for poorly graded sand. This one low plasticity clay for this one. This one, maybe these three are for poorly graded sand, and these two actually. This last one is for sand. Okay, you can even try to calculate bearing capacity and compare these formula. The reference is here. Okay, so in wet unsaturated soil, the effective stress can be obtained by this formula, sigma prime is sigma total stress minus, you remember this UA is the pore air pressure, okay, the pore air pressure, so pressure of gas, vapor, or air. And this one, this symbol, what is the name of this X? This parameter is parameter related to the degree of saturation. It will depend on the degree of saturation. This one will be 0 if the for dry soil, and it will be 1 for saturated soil. So it means for unsaturated soil, this parameter will be between 0 and 1. Okay, but this is the formula for how to obtain the effective stress in unsaturated soil. Okay, so to determine this parameter related to saturation, okay, the value of this for any specific degree of saturation, we need like experimental simulation, because this value, this parameter, the value of this parameter will change according to all type of soil. Each soil type is different, is given different value of this parameter. Okay, so experimental simulation of loading condition. So either volumetric or shear deformation are necessary. And this one, the suction, do you remember the suction? This one, we will call it matrix suction, is the key stress state variable. This one is controlling the mechanical behavior of unsaturated soil. So it is a very, very important parameter. Okay, the soil with negative pore water pressure, because unsaturated soil is the pore water pressure is negative. Okay, so the method for measuring this matrix suction are vital for predicting the deformation behavior of your soil. And these are some references. For more detail, you can check these references. Okay, they are very famous. So we go now, number 2, we are going to talk about soil water characteristic curve and water moisture retention curve. This, the soil water characteristic curve, SWCC, this one is very famous, not only in foundation actually. This one is very important also in slope stability, not only in foundation engineering. Okay, because this one depicts the relationship between volumetric soil water content, which is here theta, and soil water pressure potential, which is water pressure potential suction. Okay, see here. So volumetric soil water content, what is the meaning of that? Do you remember the water content? Water content, normally if it say water content, it we use weight of water and weight of soil to calculate water content. But volumetric soil water content, that one is using volume, the volume of water and volume of soil instead of weight. Okay, so this figure, these two A and B, this figure, so typical soil parameter for the soil water characteristic curve, SWCC curve. Okay, this A1. This one is typical curve. This one is for negative pressure, negative suction, and this one is positive pressure. Because when the pressure is negative, when the water pressure is negative, we can have suction. But water pressure positive, we cannot have suction. So this domain is the domain of unsaturated soil. But this domain is when the soil is saturated. There is no suction when the soil is saturated. Okay, so the volumetric water content is theta here. Okay, this B is showing some curve SWCCs for clay and silt and fine sand. Okay, according to the suction is changing from 0 to like 800, and how the volumetric water content is related to that suction. That will give you the SWCC. Okay, so this is soil water characteristic curve. This theta is related to the volume. We will see it very soon. The sand release water. We know that sand will release water after suction introduce drainage. However, for silt and clay, they will retain more water. This theta is given by this formula. So if you remember, for omega water content, it was weight of water divided by the weight of the soil, the total weight. However, volumetric soil water content, that one is using volume of water divided by the total volume. Okay, VW divided by V. This is this theta here, volumetric water content, volumetric water content. It will help you to know the ratio between the volume of water and the total volume of the soil. Okay, what is that ratio? And as you can see here, if the ratio is small, means the volume of water is small, then the value of suction is high. Okay, but the limit of the suction is here. This value, theta R, the residual suction, okay, this one, it will not go more than that. So once you increase the volume of water, you will see that this theta will increase also, okay, up to certain level here. Now it is 100% saturated. So V is the total volume, as I already explained, and VW is the volume of the water, okay? Let's keep this formula here, and this figure also here. So there are several empirical equations that are proposed to fit the SWCCs based on parameter in this the figure here. Okay, this is typical one. So I will just keep this one, the typical one here. This one, our theta here, the volumetric water content, is proposed, is estimated using this formula, for example. Okay, so in this formula, this E here is not the void ratio actually. This is the base of natural log. So it is a constant, 2.718, the value of this E here. Okay, and this C, this one, is the correction function, which is defined in the following equation, in this equation. Okay, it got complicated, this one. So this C is obtained by this equation, and this theta S is like the saturated volumetric water content at zero pressure. Okay, when it is saturated, zero pressure. You see the pressure here, right? So it will be here, zero pressure. And this one, A, N, and M, these are fitting parameter. By changing this parameter, you can fit the curve. Okay, so in this C of equation 30, we have here CR. This one is the suction corresponding to the residual water content. This one, okay, this value. What is the suction corresponding to this value? Okay. And I will keep the two formula here. Okay. Please don't forget that this is suction. Okay. Using the fundamental soil mechanics, the degree of saturation can be shown to be like this. You can use this formula as degree of saturation. So S will be obtained by doing theta, the volumetric water content, divided by N. Okay. Here the S is degree of saturation. Of course, N here is the total porosity of the soil. So parameter used in this equation 29 and 30 relevant in the In case of fine sand, can be obtained in this table. Okay, this one about 30 kPa, and this one theta S 0.45, A 1.948, M 1.084, N 2.708. Okay, these are just given by this reference. You can check. Also, Canadian Society of Geotechnical Engineering. Okay, I think that's all. So the most important thing to remember is that the suction is governing the behavior of, like, the deformation of unsaturated soil. Okay, and it's important for you to obtain these two formula. Okay, this one actually, because this one is just from here. This SWCC is very important, and you have several model. People are giving some equation, empirical equation, depending on the type of soil. Okay, so this one is just like a review. So when we'll start foundation in unsaturated soil, we will come back on this again. Okay, thank you very much for your time, and let's stop here and meet again later. Thank you.